In this video, we're going to talk about implicit differentiation, and up to this point, we're used to seeing two types of notation to represent the derivative, y prime and dy dx. And what this notation is saying is the derivative of the function y, and what this one is saying is the derivative of function y with respect to x. And if we had a different function, let's just say we had g of x, then using this notation, the derivative would be g prime of x. And using this notation, it would be df dx. And when we talk about implicit differentiation, we like to use this notation, which is the notation of Leibniz. And the reason is because it gives us extra information. It says that we're taking the derivative of function y with respect to x. And implicit differentiation makes a fuss about whatever variable is written here. So we're commonly used to taking the derivative with respect to x, but in the future we'll also be taking the derivative with respect to time or with respect to t. And what this is saying is that whatever variable is in here, that's going to be the independent variable. So in this case, the independent variable would be time or t, and in this case, the independent variable would be x. So let's take a look at a problem that we're used to seeing. So let's say we want to take the derivative with respect to x of x squared plus 2x plus 1. And we can do that pretty easily. We just use the power rule on each term and the derivative. Here we have the differential operator just saying take the derivative of whatever's inside. So the derivative is going to equal to 2x plus 2. And the reason why we're able to do this is because we're taking the derivative with respect to x. So x is the variable and all we have are x's here, so there's no problem. But other times, if we're asked to take the derivative with respect to x of, let's say, y to the third, now we have a problem because we have an x here. We're taking the derivative with respect to x, so this is saying that x is the independent variable. And that means that anything that is not x, so in this case y, is not the independent variable, so that means that we have to treat it as a function. And this is why you can say implicit differentiation is basically the chain rule. So because we have to treat this y as a function, the derivative is going to have a function within a function. So we're going to start with the third power. We're going to bring it down. So we get 3y to the second. And because we're taking the derivative with respect to x, that means y is a function, or at least we treat it as a function. So we multiply it by the derivative of y, which is just dy dx. So this would be our derivative. And then as we mentioned earlier, in the future, when we do related rates problems, we're going to be taking the derivative with respect to time, so d dt, and then we might have a normal looking function like x to the third. So in this case, we would have to do the same thing we did here because we're asked to take the derivative with respect to t. That means that anything that is not t, we're going to treat it as a function, so we're going to treat x as a function as well. So the derivative is going to equal to 3x squared using the power rule for the third power function. And because x is going to be treated as a function, we're going to multiply it by the derivative of x, which is going to be dx dt. Alright, so let's look at an example. So let's say we're asked to take the derivative with respect to x of the tangent of y. So here we see that we have a tangent function, and then inside we have a y, and the independent variable is x, so that means this we're going to treat as a function. So the derivative is going to equal to the derivative of tangent, which is secant squared of whatever was inside. And then because y is a function, we then have to apply implicit differentiation, which is a form of the chain rule, and multiply by the derivative of y, which is dy dx. And that's it. So here we were asked to take the derivative of an expression, but in other cases, like the next example, we'll take the derivative of an equation with multiple variables. So let's say we have x squared plus y squared is equal to 25. And this is a commonly used example when we talk about implicit differentiation. So when we have an equation, then the first thing we want to do is we want to take the derivative of both sides. So we're going to take the derivative with respect to x of both sides. And then we know that we can just take the derivative of each individual term here. So the derivative with respect to x of x squared plus the derivative with respect to x of y squared. And we know that the derivative of any constant is 0. And then what we do is we go ahead and take the derivative of these terms. So we get 2x using the power rule plus the derivative with respect to x of y squared is going to give us 2y. But because y is not the variable x is, we're going to treat it as a function and multiply the term by its derivative, which is dy dx. And all that is equal to 0. And now to find the derivative of the equation, we want to isolate dy dx. So we're going to minus 2x from both sides, giving us 2y times dy dx is equal to negative 2x. We'll divide both sides by 2y, so we get dy dx is equal to 2x is equal to negative 2x over 2y. We'll cancel out a 2, and the derivative of y with respect to x is equal to negative x over y. So when we have an equation and we want to take the derivative of that equation, and we see that we have x's and y's mixed together, then we know that we'll probably have to use implicit differentiation. So we'll go ahead and take the derivative of both sides and then isolate dy dx or whatever it may be, and that'll give us the derivative. So let's look at one more example. So here we're asked to find dy dx for the function y squared plus 2y is equal to x to the third plus 4x squared plus 8. So here we notice that we have y's and we have x's, and we see that we can't easily isolate the y. So we're going to go ahead and take the derivative with respect to x of both sides. Once we do that, we're going to isolate dy dx, and then we'll get the derivative. So we'll take the derivative with respect to x of y squared plus 2y, and that'll be equal to the derivative with respect to x of x to the third plus 4x squared plus 8. And then we know that the derivative of a polynomial is going to be the derivative of each individual term. So on this side we have the derivative with respect to x of y squared. So we're going to get 2y, but then we have to multiply it by dy dx, the derivative of y, because y is not the independent variable, so we treat it as a function. Similarly here we have a 2y, its derivative is 2, but because y is going to be treated as a function, we're going to multiply it by the derivative of y, which is dy dx. And then on this side, we're asked to take the derivative with respect to x of x to the third. That's just going to be 3x squared. They both match, so we don't have to worry about implicit differentiation. Similarly here, we bring the 2 down, we get an 8x. We don't have to worry about implicit differentiation. And then we see that we have a constant, and the derivative of any constant is 0. So we took the derivative of both sides. So now we're going to isolate dy dx. So we'll do that by factoring it out. So we get dy dx times 2y plus 2 is equal to 3x squared plus 8x. And then we'll go ahead and isolate dy dx, and we'll do that by dividing both sides by 2y plus 2, giving us dy dx is equal to 3x squared plus 8x divided by 2y plus 2. And that's it. This is the derivative.